Oxidation-reduction reactions, aka redox reactions, is going to be the topic in this lesson, and we'll start by defining oxidation and reduction. We'll find out that these are just electron transfer reactions. One species is going to lose electrons, one species is going to gain electrons, and we associate each of those names with one of those. We're going to find out that determining oxidation states will be pivotal here, because that's what we're going to use to determine who gains and who loses electrons. So we'll go through those rules for assigning oxidation states. And then finally, we'll finish this lesson off talking about single replacement reactions, a type of redox reaction. And we're going to learn about the activity series, which is going to help us determine whether or not these single replacement reactions actually happen or not. The word we use is whether or not they are spontaneous or not. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. This lesson is part of my new general chemistry playlist. I'm releasing these lessons several a week throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You can find those courses at chadsprep.com. All right, let's dive into this here. So we've got to start with an example of a redox reaction here, or an oxidation-reduction reaction. The one I've given here, and we've got to define some terms here, which are going to be oxidation and reduction. And oxidation is the loss of electrons, reduction is the gain of electrons, and we have some lovely little mnemonics here to help us remember those. And oxidation is the loss of electrons, reduction is the gain of electrons. So you got oil rig. But my personal favorite is Leo the lion says grrr. It's just more fun to say for one, but also it includes the letter E, which stands for electrons. Lose electrons oxidation, gain electrons reduction. Whereas here we're just saying oxidation is loss, well, loss of electrons. Reduction is gain, well, gain of electrons, but here it's incorporated that we're talking about electrons in the mnemonics. So that's going to be important here. So if we take a look here, one of the first rules we'll learn about oxidation states is that any element in its elemental form, not a charged form, but elemental form, is in the zero oxidation state. So in this case, that's going to correspond here to both zinc on this side and copper on this side. And we'll also find out that for monatomic ions like the copper and zinc ions here, their oxidation state corresponds to their charge here. So in this case, the oxidation state would be +2, and in this case, the oxidation state would also be +2. And so what we're going to look at for is the change in oxidation state as evidence that electrons have either been lost or gained. And so in this case, you got to think about this a little bit different than you normally think of losing or gaining something. If you lose money out of your bank account, then the value of your bank account goes down. If you gain money of your bank account, then the value of your bank account goes up. But when you lose electrons, electrons are negatively charged. And if you lose negative charges, your charge or oxidation state actually goes up. And when you gain electrons, gain negative charges, your oxidation state or charge goes down. And so it seems a little bit backwards, but that's where that terminology comes from. So just keep that straight. And so if we take a look at what happens with zinc here, zinc is going from 0 to +2. It's getting more positive. And so we might want to think, well, did he lose negative charges or gain negative charges? Well, again, if you gain negative charges, you're not going to get more positive. So in this case, he must have lost negative charges. And we would say that zinc here got oxidized. Now, on the other hand, if we take a look at copper, copper is going from copper 2+ to copper in the elemental form. So from the +2 oxidation state to the 0 state. And now we can see that he has gained 2 negative charges, 2 electrons. And so we say that copper 2+ here has been reduced. And if you notice, that's why they actually call it reduced, because it's your oxidation state that's getting reduced. Your oxidation state is getting lower. So cool, whenever you've got an oxidation-reduction reaction, you're always going to have at least one oxidation and one reduction. Technically, you can have more, but you're not likely to encounter them just yet in this chapter. I will warn you, we will have an entire chapter on electrochemistry, which is going to be really all centered around oxidation-reduction reactions, but at the very end of this playlist, towards the end of the Gen Chem 2 topic. So this chapter is really just, or this lesson in this chapter is just going to introduce the topic here of oxidation-reduction reactions. Now on the study guide here, I have provided some rules for determining oxidation states. And when we cover this again in the electrochemistry chapter at the end of the playlist, I'll give a little more robust set of rules here. But for now, this is a pretty adequate set of rules. And you follow these rules in order. And the first rule just says that if you have an element in its elemental form, it is in the 0 oxidation state. And so in this case, these are the only 2 elements that are on the board. So everything else up here is either a compound or a polyatomic ion. And so these are the 2 elements. So one's monatomic, one's diatomic, but notice there's no charge on either one of them, and that's the evidence that you've got an element in its elemental form, and they're in the zero oxidation state. That is rule number 1. Now, rule number 2 talks about monatomic ions. So not polyatomic ions, but monatomic ions, which implies you have an ionic compound like NaCl here. And these are both monatomic ions, not polyatomic ions. And when you've got monatomic ions, they just get their normal ionic charge. Now, key thing you're going to have to realize, though, is that if you've got transition metals, or at least non-group 1 and group 2 metals, that can take on variable oxidation states, variable charges, you'll have to figure them out based on what anion they're with. So, but in this case, sodium is from group 1, and in an ionic compound, they're always +1 as ions. Chloride being a halogen, so they're always -1 as monatomic ions, and voila, there you go. So monatomic ions just based on where they're located on the periodic table, or again, if we had a transition metal, like if we had copper, let's say, and you had CuCl2, so copper can sometimes be +1 and +2, and it depends on context. Now, I don't expect you to know that it's either +1 or +2 for most students, but what you could figure out, though, is that chlorine as a monatomic ion, the chloride ion, is -1, and there's 2 of them for a total of -2, and therefore the copper must be +2 to balance. And that's what I mean, that you'll have to figure out the transition metals oxidation state based on what anion they're with and how many and stuff. So, all right. We'll move on to sodium bicarbonate here. And so in this case, sodium is still a monatomic ion, and we still have one of them, and he's still going to be +1, but now we've got bicarbonate, and that's going to be a little bit of a pain in the butt. And so the way this works, after you look at elements in their elemental form, which obviously we have a compound here, so none of those, and after we look for monatomic ions, we got sodium, he's one of those, then you're going to start looking for some of the regular nonmetals, if you will. And so some of the ones I put on your sheet is oxygen is usually -2, unless it's part of a peroxide, in which case it's -1. We've got hydrogen, which is typically +1 when it's combined with any combination of nonmetals. And when it's with only metals, that's when it ends up being -1. And so actually we can assign him now. So hydrogen's with some combination of nonmetals. Had this just been sodium hydride and with hydrogen with a metal only, that's when it would have been -1. But if it's present with any other nonmetals in the compound, it's going to be +1. All right, and we got fluorine is going to be -1 always in a compound when it's not in its elemental form. And then halogens are usually -1 except when they're part of the oxoanions. With oxygen, then they're going to be something else. All right, so we said that oxygen, when he's not part of a peroxide, is -2. We'll go from there. And then one thing you should note, we're going to keep a tally here. There's 3 of these -2s. That's a total of -6. There's just 1 of the hydrogens. That's +1, so that's +1 total. And there's only 1 of the sodiums. That's +1 total. And the idea then, the last rule just says that for a neutral compound, all of the oxidation states have to total up to 0. And again, that factors in not just the individual oxidation state per atom, but for how many you actually have in the molecule, or in the compound, as I should say in this case. And so in this case, carbon, we can see, has to balance out the rest of this. We got more negatives than positives, so he's going to need to be positive. And in this case, we can kind of see that he's going to need to be +4. And so this is kind of the approach we take. Assign, any monatomic ions in the compound, then go and look for the regulars like oxygen, hydrogen, halogens, and then anybody that's left over is going to have to balance out the rest of the charge. Now, you could also make an algebra equation out of this. You could just say sodium plus hydrogen plus carbon plus 3 times whatever oxygen is has to add up to 0. And so in this case, we figured out that sodium was +1, hydrogen was +1, carbon we didn't know yet, he's the last one to assign, and then oxygen was -2 each. And if this all has to add up to 0, then we can figure out algebraically, solving for this as kind of like its x, if you will, solving for carbon, it would indeed come out to +4. Okay. Let's get a little more challenging here. So here we've got carbon dioxide, and in this case, there's no monatomic ions because it's not an ionic compound here. So definitely nothing in their elemental form because it's a compound, and no monatomic ions. So then we look for the regulars. So oxygen, hydrogen, halogen, and we've got oxygen. So we're going to make oxygen -2. Cool. And carbon's just going to have to balance the rest of this out. This is a neutral compound, so it's going to have to balance it out to 0. And that's going to make carbon here, since there's 2 of these -2 oxygens, a total of -4, carbon's going to have to be +4 to balance that out. Okay, this is hydrogen peroxide. And I want to point this out because it is a peroxide. And this is that case with a peroxide where oxygen is -1 instead of -2. So in a compound, oxygen's almost always -2. but peroxides are the most notable exception where it's -1. Now, how do you recognize a peroxide? Because a lot of students memorize it when you have two oxygens. Well, we just had two oxygens. So, and this is not often spelled out all that well, but the way this works, so oxygen, well, in this case, hydrogen's a regular, but oxygen is too. But the way you're going to recognize it as a peroxide is one, it does have two oxygens, and it's going to be with either hydrogen or a group 1 metal is the most common by far. And so here it's with hydrogen, two oxygens with hydrogen. Great, that's a peroxide. And so in this case, that's going to make oxygen -1. And we said that hydrogen here is always +1 when it's with nonmetals. And so this always, it'd be the other way to figure it out. If hydrogen is always +1 with nonmetals, well, to balance this out, then the oxygen would have had to have been -1, not -2, for this to balance out to 0 total. All right, I want to make sure we did one example of an ion rather than a neutral compound. And the big difference here is that instead of all the individual oxidation states summing to 0, in this case for sulfate ion, it's going to sum to -2. All right, so nobody in their elemental form because it's a polyatomic ion, not an element. And in this case, we've got no monatomic ions. It's all, everything here is just a simple or simply part of a polyatomic ion. So then we look for the regulars, and oxygen is the regular here and is going to be -2. So, and in this case, there's 4 of them, which means we get a total of -8. Now, one thing to note, you might get a question on a test that says, what's the oxidation state of oxygen? And oxidation state is always defined per individual atom. And so in this case, the right answer would be -2, not -8. So there is a total of -8 charge here, but oxidation state per oxygen is still -2 per oxygen. That's, again, how oxidation state is defined. And so then finally, sulfur is going to have to balance the rest of this out. But again, if we were balancing it out to 0, well, then we could see he needs to be +8. But we don't need to balance it out to 0 now. We need to balance it out to -2, in which case we can see that sulfur is going to have to be +6 instead, because 6 minus 8 is -2. And once again, you could make an algebra equation out of this, and you could say sulfur plus 4 times whatever oxygen is doesn't add up to 0 now, but adds up to -2. And we already figured out again that oxygen was -2, and 4 times -2 is -8, and you can solve it algebraically and get sulfur big, +6 in that fashion as well. All right, so now we want to spend just a couple of minutes identifying these oxidation-reduction reactions, aka again redox reactions. And the question I'm giving you here is, which of these 4 is or are redox reactions? So, well, the hallmark again of a redox reaction is that somebody loses electrons, somebody gains electrons. They are electron transfer reactions. And the hallmark of, having species both lose and gain electrons is a change in oxidation state. And so one way you could approach this is you could just start assigning oxidation states for all the elements in all the compounds in all 4 of these reactions. But that's going to be kind of a slow and laborious process. Not the fastest if you're trying to do this in a hurry and in a pinch on an exam. So we're going to go through some shortcuts a little bit of how you might pick out some of these redox reactions and how you might eliminate some of these as not being redox. And so first thing I'll tell you is this. Look for elements in their elemental form. That's the first thing. So like if we look at the first one here, we've got both magnesium and oxygen, both in their elemental form. And odds are they're not going to be in the elemental form on the other side. In fact, they're not. Now they're part of a compound. And if you're in the elemental form on one side, well, that means you're in the 0 oxidation state. And if you're not in the elemental form on the other side, well, that's going to typically almost always mean you're not in the 0 oxidation state. And so we don't even have to assign oxidation states, but we've got some that start out as 0 and end up not 0. That's a change, and that is a redox reaction. So yes, this is a redox reaction. And if you wanted to figure it out, so in this case, you're going from 0 in magnesium's case to +2 and he got oxidized, whereas oxygen's going from 0 to -2 and he got reduced. All right. So the next one here, we don't have any elements in their elemental form, so we'll skip it. And the next one, we don't have any elements in their elemental form, so we'll skip it. And the last one here, we've got copper in his elemental form, so he's in the 0 oxidation state, and silver over here, both in their elemental forms. And so, copper's in his elemental form here, he's part of a compound here, not in his elemental form, he changed. Don't have to figure out that he's +2 and went from 0 to +2 and got oxidized. All I have to see is that he's 0 and now he's not 0. That's a change, and this is going to be a redox reaction. Now, we can take this a step further. So it turns out that this you might recognize as a single replacement reaction. We're going to spend a little more time talking about those in just a little bit. But single replacement reactions are a type of redox reaction. So they are always going to be redox reactions. So if you see this, even if you didn't recognize that you had stuff in the zero oxidation state, but you're like, oh, that's single replacement, that's redox. Great. So not all redox reactions are single replacement, but all single replacements are redox. All right, so far so good. We instead of having to assign all the oxidation states, in these two at least, we just quickly figured out that yes, they are redox because we had elements in their elemental form in the reaction. All right, now for the other two, you might recognize what kind of reactions these are. This first one is a decomposition reaction, going from one species to two species. And then this next one you might recognize as a double replacement reaction. So where cations and anions are trading partner. And if you recall, that was actually the object of the last lesson. And so in this lesson, we're talking about redox reactions. In the last lesson, we talked about double replacement reactions. And the reason they're taught in separate lessons is because they're separate. Double replacement reactions are never redox. And so in this case, once you recognize it as double replacement, you'd be like, oh, no, that's not redox. So you could take it that far. If you actually went through to assign things, what you'd find out is that here silver's +1 and here silver's still +1. Here chlorine's -1 and here chlorine's still -1. Here hydrogen's +1 and hydrogen is still +1. And as long as the polyatomic ion doesn't change, it's nitrate and it's nitrate, so you could figure out that nitrogen and oxygen are going to be the same, but you could also go a step further and figure out that oxygen's -2 and nitrogen's +5, and that is still true over here. But notice that's a lot of work. And I've got a lot of practice, so I can do it quickly, but it's a lot of work assigning all those oxidation states. But again, if you recognize it as a double replacement, you can be like, oh yeah, those are never redox. All right, now I don't have a rule for this decomposition reaction for you. A lot of decompositions tend to not be redox, but I don't know that I can say with any kind of absolute definitive statement that they're never redox. I just don't know that that's true. So if you go and assign oxidation states, in this case, you've got no elements of their elemental form, but you do have monatomic ions. And here calcium is a monatomic ion, and as a monatomic ion being in group 2 is +2. Still a monatomic ion right there, so it's still +2. So on the other side, you also got oxygen as a monatomic ion, and he's -2, being 2 elements away from the noble gases. All right, for the rest of these, you want to assign the regulars now, either in a molecular compound or as part of a polyatomic ion. And again, the regulars are oxygen, which is typically -2, like he is here, as well as here. And if we had any hydrogen or halogens, we'd be starting to look for those as well, but we don't. And now in both these compounds, we only have one element left. And this one's going to be a little easier. You have 2 oxygens that are -2 each for a total of -4, so carbon's going to have to be +4. And over here, we've got 3 oxygens that are -2 each for a total of -6. The calcium's +2. We need an additional +4 to balance this out to 0. And so in this case, nobody changed. Calcium stayed +2, oxygen stayed -2, and carbon stayed +4. And with no changes in oxidation states, this is not a redox reaction. Cool. So you're going to want to get very proficient at assigning oxidation states, and this is one of the reasons why. Not only can you expect on the exam on this section to just simply have to find the oxidation state of a certain element for a certain question, but you might also have to identify when a reaction either is or is not a redox reaction. So now we've got to spend just a few minutes on single replacement reactions, which again are a type of redox reaction. And before we discuss these single replacement reactions, I just want to point out what is often provided in this context, which we call the activity series, which is on the study guide there. And the way the activity series works is they put the most active metals, or in this case, what we call the most reactive in an oxidation reaction, at the top of the list, and the least reactive at the bottom. And so we like to say that they get more easily oxidized as they go up the list. So if I gave you, say, lithium going to lithium +1 plus an electron versus potassium going to potassium +1 plus an electron, and I said, which of these reactions is more easily going to happen? Well, in this case, again, you went from 0 to +1. Those are both oxidations. And in this case, I can see that lithium is more easily oxidized than potassium. And so this first reaction would be the more likely one, the easier one to happen, if you will. And so this is going to become useful when we start talking about these single replacement reactions in just a second. All right, so once you're given this activity series, again, you're given it for a purpose, but you might just get a question on your exam that just says, hey, which of the following is the most active metal, or which of the following is the most easily oxidized? And in either case, you're picking the one that's highest on the list. All right, so that's your activity series. We typically don't make students memorize this. This is almost always something that students are provided with if they're going to need it. All right, so we've got 3 single replacement reactions here. And if we look, we got, in this case, they call it single replacement if you look, because here we've got a happy couple, H and Cl, and here magnesium's all alone. But magnesium and chlorine are going to end up together, and then hydrogen's going to end up all alone. And so magnesium is replacing or displacing hydrogen in being with chlorine. And so that's where it gets its name, single replacement, single displacement. And if you look, what's nice is there's another way to look at this that might make it easier to remember, but it's not going to be quite as helpful as from an understanding perspective. But it's the way I like to look at this initially. And I like to say, you know, magnesium thinks chlorine is so cute, and magnesium would like to be with chlorine, but hydrogen's with chlorine right now. So magnesium is going to replace chlorine in this relationship and leave hydrogen all alone. It's kind of sad. So here's the deal, though. The only way this is going to happen, the only way magnesium is going to replace hydrogen in this relationship is if magnesium is better looking than hydrogen. So, and the best looking metals or elements, because hydrogen is not a metal, the best looking elements are at the top of the list. Now, one thing to note, I didn't have room, I didn't space this well enough to get the entire activity series. There was a couple of metals left off the bottom, but this will work for our purposes. But in this case, magnesium is a better looking metal than hydrogen. And so, yes, this reaction is spontaneous, we'd say. It will happen. So when you drop a solid piece of magnesium in aqueous hydrochloric acid, what you'll find is that the solution starts to bubble as a gas is produced, in this case that hydrogen gas, and that magnesium solid dissolves away into the solution, turning into part of the aqueous part of that solution. Cool, so it's spontaneous. All right, so if you look at what's really going on in the real appropriate perspective here, is if you look, magnesium starts out in the 0 oxidation state and ends up +2, whereas hydrogen starts off in the +1 oxidation state and ends up at 0. And so the question is, who's getting oxidized, who's getting reduced? Well, again, the one getting reduced is the one where the oxidation state gets reduced, and that's hydrogen, going from +1 down to 0. That's a gain of electrons, gain of negative charges. So, whereas magnesium is the one being oxidized. And that's the one we're really going to focus on, because that's what the activity series is going to give us some details about. And so the way this works, and the way you should formally, theoretically understand this, is that the species that gets oxidized needs to be the species that is more easily oxidized. And so in this case, out of magnesium and hydrogen that are both either gaining or losing electrons, it is the magnesium that is getting oxidized. So therefore, magnesium has to be higher than hydrogen on the list, because the species getting oxidized has to be the species that is more easily oxidized. All right, so if we look at the next one here. So again, I like to think that the one that starts out all alone has to be better looking to displace the other one or replace the other one. And so has to be better looking for the reaction to happen. In this case, is copper better looking than zinc? Well, here's copper down here, here's zinc up here, and actually zinc's better looking. Copper is not better looking. And so this reaction, we can write it all day long, but it's not actually going to happen. And we would say that it is non-spontaneous. And so in this case, if you take a solid piece of copper and put it in an aqueous solution of zinc nitrate, it will just sink to the bottom and sit there. This reaction as written does not happen. Cool. Now again, the way you're supposed to look at this is you're supposed to look and say, okay, copper goes from the 0 oxidation state to +2, and that means he's the species getting oxidized. And so he's got to be higher on the list than the species getting reduced for this to happen. And it's zinc going from +2 to 0. That's obvious reduction. And once again, though, the species that's getting oxidized is not the one that's more easily oxidized, and that's why this reaction is non-spontaneous, why it's not going to happen. All right, one more. So this one, the spectator ions have been eliminated. Like in this reaction right here, the nitrate ions are actually spectator ions and wouldn't appear in the net ionic equation. In this one up here, the chloride ions are spectator ions and wouldn't appear in the net ionic equation. And if the spectator ions are left out, it's hard to see why they even named it single replacement or single displacement here. And remembering that the best looking metal, is higher on the list doesn't actually help you, because there's no happy couple anywhere on here. And so you actually do need to understand it from an oxidation perspective and say, okay, who's getting oxidized? And typically that's the one that starts off in the elemental form, in the 0 oxidation state. That's going to be getting oxidized, as is the case right here. And so manganese is going from 0 to +2. He is the species getting oxidized, where it's the nickel that's getting reduced and going from +2 to 0. And again, the species getting oxidized has to be the species that's more easily oxidized and higher up on the activity series. So what we're saying is that for this reaction to be spontaneous, manganese has to be higher on the list than nickel. And in this case, manganese is right here, nickel's right here. Manganese is indeed higher on the list than nickel, and this reaction is going to happen. It is going to be spontaneous. Cool. So quickly, in a pinch, if we're not showing the net ionic equation, but just the complete molecular equations, then by all means. So whoever's doing the replacing, whoever starts out all alone, has to be higher on the list. Life is good. However, you really do want to understand it from an oxidation perspective. And again, whichever one's getting oxidized has to be the one that's more easily oxidized and higher on the activity series. Now, if you found this lesson helpful, a like and a share goes a long way to making sure other students get to see it. And if you're looking for a lot of practice or final exam reviews and practice final exams, check out my General Chemistry Master Course. I'll leave a link in the description. A free trial is available. Happy studying.